All right. Hey everyone. Hello. Welcome to Discovering Dark Matter towards better Android malware heuristics. We're going to go over a couple of things today. We're going to try to teach you how to perform basic Android malware analysis. I'm going to focus on APK analysis, runtime analysis of Android apps, and then static code analysis, and how those two things in conjunction can basically take you from not knowing a whole lot about Android analysis to being able to do some more serious stuff. Matt's going to talk about a deeper understanding of the Dalvik virtual machine as well as DexCode. It's pretty interesting. And then Jimmy is going to talk about how our tool can help, but since he's not here, we're going to go ahead and do the best we can with his tool. So, we'll just dive right in and do our best. So my name is David Shaw. I'm the Senior Director of Engineering at Redspin, a small computer security company in Santa Barbara. Traditionally, I've specialized in application and network security assessments. I was a technical editor of the MMAP6 Network Exploration and Security Auditing Cookbook, which is a pretty good primer for the MMAP scripting engine. And I'm on Twitter, D. Shaw. Now you might notice that my background, as well as sort of my specialties, aren't around Android malware analysis. And that's actually pretty important for this talk, so that we can actually take someone who doesn't have a whole lot of experience doing that and teach them some stuff. So I'm not a professional malware researcher. I'm not a reverse engineer. I'm definitely not an Android expert. I actually have an iPhone. I don't even have a physical Android device. It's pretty embarrassing. And I'm not a Java developer. So, So let's start in the beginning. We're just going to define the problem of mobile malware because it's actually a little bit different than conventional malware in a couple different ways. So there's a big block of text, and don't worry about that. We're going to define malicious software as any software that either through the abuse of granted permissions or via traditional exploitation conducts activity that may be considered malicious or mishandled. Or maybe said more programmatically, permissions abuse or exploitation or security misconfiguration yields something that we would say is malicious in some way. Now, the reason that this is different than conventional malware is that if we have, say, an app that reads through your address book, uploads all your contacts to some arbitrary server, and then periodically blasts out text messages to all of your contacts saying, hey, we got some photos for you to view, look at my new bikini pictures, would we consider that malware if it's propagating itself? Now, conventionally we would. This is pretty much exactly what the Melissa virus did back in the day, except with email rather than text messages. So we'd say, okay, it's propagating itself, it's malware. But we don't say that if it's a social network that has 10 million users. And yes, we know that this is an iPhone app, but it's the most recent example of, okay, well, we've given this app permissions, we think it's something that we want, and it's actually abusing those permissions, and it's texting the entire phone book at 6 a.m. or doing something that we would say is bad. And the way that it can do this is that it's abusing permissions that you've actually given it. You're saying, yeah, you can read my contacts, yeah, you can send out text for me, yeah, you can do all this for maybe somewhat legitimate purposes at the time, but it turns out that it's actually abusing those permissions. So we have a screenshot of an app that has all of these permissions. It can access your personal information. It can send text messages, which is actually labeled as services that cost you money. It can access your Find GPS location. It can delete things on your USB storage. It can basically do everything. Now, traditionally, we need to actually exploit a device or an operating system to get these permissions. But as we found out with, say, SSL problems, users will generally just click yes unless they see something that's really a big red flag. So since everything's sort of a social network these days, they said, oh yeah, I'll give it internet access. Oh yeah, I'll let it search through my contacts. I'll let it do all these different things that really it probably shouldn't do. So now that we know that there are different permissions that can be abused, we need to basically find a needle in a haystack. Because we have, about 1 million apps, more than that now, currently on the Google Play Store, which is a lot. And we know that many of those apps legitimately need the permissions that they request. So where do we start? How can we begin this first phase of analysis? Well, generally we start with a really big list of APKs. And in order to start with APK analysis, we need to understand a little bit about how an APK is structured. Basically, it's a zip file. It contains a bunch of information about the app itself, and it can easily be manipulated and read, which is, of course, pretty helpful. In particular, we're going to talk about Android manifest.xml, which is basically an XML file that tells Android OS what the app's called, what permissions it's going to request, what it's going to do. And more specifically, the manifest permission lines, which is saying, I'm going to ask for these permissions. Now for this talk, we're going to be looking at permissions that relate to data read and write access on the phone, data at rest, and network read-write access over the network, which is just data in transit. So this is a big block of text, and I'd like to point out at this point that at the end of the talk, or at the end of my part of the talk, there is a URL for all of the one-liners and shell scripting and this big block of text that you can download. So you don't need to do anything weird with it. But if you look at this, reading the phone logs, internet access, write to the social stream, send and then write and then send SMS, persistent activity, install packages. There's a lot of really potentially bad permissions here that you want to make sure that you're looking at. But so this is a lot, and it's sort of out of scope for the whole talk. We narrowed it down to 6. We're going to call this perms.txt. I'll actually be using that a little bit later. So we're looking at read contacts, call phone, install packages, write and then send SMS, and unrestricted internet access. So we have this large list of APKs that I was talking about, and now we have perms.txt for what we're looking to find. And we need to parse the data out of Android manifest.xml. Well, fortunately, it's pretty easy to do that using a combination of open source tools, as well as a little bit of shell scripting. APK tool is a freely available Java tool. You can run it pretty much anywhere. We've done analysis on Linux, Windows, and Mac, so you can get it anywhere. It's really easy to use because we're pretty much only using one function there, the decompile function, to take an APK and break it down into its components. So basically, we're just using it as unzip on steroids. So knowing that, we can actually go ahead and go through our directory, and again, these lines are on the net afterwards. So for each element in our APK directory, we run the Java jar apk tool.jar with the decompile command for that element, and that yields a bunch of directories of decompiled APKs. From there, we can actually say, for each element in perms.txt that we went over earlier, and see if they're present in each of those folders, Android manifest.xml files. So from there, you can actually get a list of, okay, we went from, let's say, 1,000 apps, which is about what we used for our original sample size, and then now we know, okay, which ones are using these permissions that we're actually trying to focus on. And obviously, if you're looking for particular things, you want to change the contents of perms.txt. The reasoning behind this is that you can't use permissions that aren't granted, and you can't grant permissions if they don't ask for it at a certain point. So we've gone from this large list of potentially abusive apps to a shorter list of apps to inspect more closely, which is really helpful when you're trying to do sort of broad spectrum malware analysis and to see what apps are doing things that they shouldn't be. As a side note, this works for not just malware, but like I said in the first slide, misconfigured software that maybe they think it's okay to take your contact list and shoot it out somewhere in plain text, but if you do that on an open wireless network where you don't know what's actually happening or it does it in the background, then you actually are at risk. So now that we have the short list, we can actually move into part 2, which is runtime analysis. We're actually running the app and seeing what it's doing at the time. So the Android SDK comes with an emulator, which is great. You don't need to have a hardware device. It's basically designed so that when you're writing apps, you can test it. It's really easy to set up. Android create AVD with name test, type Android 17. And at first, for our first layer of sort of inspecting this, a man in the middle is unnecessary because Android actually lets us capture all the traffic. So our sort of methodology here is going to be to run the emulator, install the APK, capture the packets, and then perform analysis on that. So you can see here you run it with just the TCP-DOM flag, pretty straightforward, and it actually dumps out PCAP. You can then use ADB to install, in this case we did Instagram 106. And then you want to use the app normally for greater than 5 minutes. The 5-minute threshold is you want to make sure that if someone's writing a malicious app, intentionally malicious app, they're going to wait more than 5 minutes to do anything really bad if it's on the Google Play Store, because Google Bouncer actually analyzes these apps for 5 minutes to see if anything is going on there. So it's actually pretty interesting that we know that now and they know that now, so it's diminishing returns on the effectiveness of Google Bouncer at that point. And from there you have the PCAP created. And once the PCAP is created, you can actually use a more standard set of tools, like for example TCP-DOM. So here you can see that we're running TCP-DOM and reading from the file that we just created. And we're saying that the source is the Android device and the destination net is not the Android device. So in other words, okay, what host is it connecting to? And using awk and then sort unique to say, we want a list of unique combinations of remote hosts and remote protocols in the time that we analyze this. So we came out with a couple of EC2 servers, a couple of Google servers, a random NTP server, I don't know why that was there, and a cloud run load balancer. So at this point, this is pretty benign. But some malware, you'll see, oh wow, why is it connecting to 18 hosts in China? Why is it connecting to arbitrary hosts every minute? What's happening? Is it doing something weird? Now at this stage, we didn't see that, but this is the first layer of, oh, something might be really wrong here. If you use a little bit of regex here, and yeah, I know that's not super human readable, basically what I'm trying to do here is get a protocol count. So I'm saying for each of the requests made during this probably about a 10-minute period that I was testing, what protocols are being used to connect to a remote host. And we came out with this. Okay, we have 13 HTTP requests, 532 HTTPS requests, and then that random NTP request. Okay, so if you're going to do standard traffic analysis, you'll probably notice the problem here, because you have this packet capture, but what can you really do with it when, in this example, 97.43% of the requests are SSL encrypted? Because crypto is great, big proponent of crypto, but for the same reason that I can't read your SSH tunnel right here at BSides, I also can't see if these requests are sending sensitive data or if they're just updating or checking for news or whatever. So in order to do that, we need to do some SSL interception. And Android doesn't play along in the same way that it does with TCP flag. It basically becomes irrelevant once you notice that the traffic's all encrypted. And we notice that probably for 99% of malicious traffic is going to be encrypted. We think that malware authors do the easiest thing first, and if the easiest thing is going to be plain text, sometimes we'll get a hit there, but overall, not so good for that. And installing a CA isn't feasible for quick analysis because, again, we're trying to do this iterative process, but we will get to that a little bit later. What we can do is basically use DNS redirection in combination with an intercepting proxy to sort of fool the Android devices into thinking that it has a valid SSL cert when it doesn't. So there's a tool to do this. It's open source. It's called Android Proxy. Again, cross-platform. Its only requirement is the Twisted library. And it basically uses DNS trickery to allow SSL interception. So taken from their Google project page, you can see that the emulator is basically making a DNS request for google.com. Android Proxy is sending back an arbitrary IP address that is keeping track of, saying, oh yeah, google.com is 1.1.1.3. Then when the emulator sends the connect request, it's actually rewriting that connection to our intercepting proxy, which both in this screenshot and in our analysis was burp sweep. So doing that, we can basically run the emulator. Again, all these commands will be online. Point the HTTP proxy flag to Android Proxy, as well as specify to use the localhost DNS server. Obviously, you need to turn off any other DNS server you may have running. And then burp suite or another intercepting proxy listening on localhost 8080. So from here, you can see that I'm at encrypted.google.com, searching for ponies. They're small horses. They're cute. And it's great. Okay, that worked. You can see Android Proxy in the background actually rewriting those DNS requests and then connect requests, forwarding to the intercepting proxy, which yields basically in the end, you can see, oh, well, there's burp reading my encrypted connection, or allegedly encrypted connection. Here's the problem though, because that sounds great. It often pops up a warning like this. And it says, hey, something's wrong. You want to continue? Because I don't think the certificate is what you think it is. Here's the good news. When you see this error, things are great. It means that you can continue, you can hit continue, you can just keep going, and it's fine. It'll actually let you do that. Here's the problem. When we were talking about our suspicious permissions earlier, we noted running a background process. But what if a process is running in the background and it actually doesn't give you the choice of doing this? Maybe you do your analysis and you click continue a couple times, you don't notice anything strange, but you're pretty sure that the app is doing something suspicious. How are you going to figure that out? Or even if you can detect that it's running a background process. Well, from there it gets a little bit more tricky, and you actually need to install your own SSL certificate. So again, Google sort of helps us out in maybe a backhanded way by having the make SD card command. We can basically create an image file for an SD card, mount it with the -SD card command, and then use ADB to push the cert onto the phone, then install it manually. And that persists post-reboot, so you only need to do it once. And then that works a lot better. And you can just run the HTTP proxy directly to whatever your intercepting proxy is. Again, we use burp, so localhost 8080. So here you can see that we have the ports rigorously installed, but it's a little bit alarming that Android does make the differentiation that it is a user-installed cert. Now, so far we haven't seen malware or malicious programs that are declining user-installed certs, but we're thinking that's probably going to happen down the road. For now, it's fine. Once it's not, then it's going to have to go back to actually figuring out a way to push that into a system-installed cert, even though it really isn't. Okay, so now we've seen basic runtime analysis, and we're saying, all right, again, we're focusing on the network, so What's it connecting to? Is it doing anything suspicious? Is the traffic that it's sending that may be SSL encrypted, is it your contact list? Is it, your pictures? Is it your passwords? Is it the contents of your USB storage device? Well, what is it? And we can actually see that. But it doesn't always happen that during the time that you happen to be running the analysis that you're seeing anything suspicious. So from there, we're going to go into some brief static code analysis. And keep in mind that this was never, my specialty. So we're going to look at basically DEX files, Dalvik executables that run on the Dalvik virtual machine. Matt's going to talk about that in more significant detail in a couple of minutes. But the important thing about a DEX file is that it's easily convertible to the Java jar format, which allows us to use our more standard tool suite when we're actually performing that analysis. So we can use a free open source tool called DEX to jar to basically say, okay, we're going to run that against this SpyU malware. It basically just spits out a jar file, super easy to use. Then we use JDGUI to open the jar, save all the sources, which saves as a zip file, and unzip that. Now from here, we can actually search for remote hosts that may be hard-coded, even if dynamic analysis failed to detect them. So this can be useful if certain actions trigger a pre-designated network connection, or maybe it only checks for CNC on, at midnight on the 1st of every month or something like that. Because unless you happen to get lucky and you're using the runtime analysis at that particular time, you wouldn't have seen that in the dynamic analysis. So using this grep statement, it's a recursive grep, case insensitive, to look for any 4 numbers that are separated by dots, basically an IP address, or HTTP with an optional S, colon, in any of the source files. So in this particular piece of malware, we saw, okay, well, copy9.com is hard-coded a bunch of times, and that's about it. No hard-coded IPs, just this one URL, which seems a little bit weird. Maybe it's going to pop up an alert. We didn't really know. And this, as I mentioned, can feasibly locate hard-coded backdoors and command and controls, but we're trying to make it a little bit more automated. Since right now, using JDGUI, as the name implies, it's a graphical tool, and it's really irritating when you're running everything via shell scripts and in an automated fashion, and then you have to run JDGUI. So it's not just hard-coded IP addresses. You can actually look for anything that's really sensitive that's going on. For example, URIs of different things on the phone. So we looked for the content URI, and we found, okay, well, this app that we'd already seen had requested the permission to go through your text is actually parsing through the content of SMS inbox, which is basically saying it's reading your text messages. So we're saying, okay, now we know that not only did they request the permission, they're actually going to use it. And this is actually an important differentiation because a lot of the false positives that we've seen are apps that really just request permissions thinking, well, maybe one day down the line we'll need this. Maybe, maybe we'll want to make it a social network next year, and we'll just request it now so people get used to that, which is, really irritating when you're trying to find malicious apps. And this also works for, a lot of important keywords like the SMS, URI, phone keyword, socket keyword, etc. Basically, you're going to go through the Java and Android docs and see how that works. So where we actually ended up finding sort of the key element here was on the SMS manager tool. So we saw that not only is it a suspicious method name, which is send data of SMS to website, we actually saw it as basically going through the SMS inbox, taking that, posting it to a website, to the web logs, log SMS post.aspects, and basically every time you get or you receive or send a text message, it's actually posting that somewhere. Now this particular piece of malware is one of those commercial malware for sale. It's, hey, is your spouse cheating on you? Download this and see everyone they're texting. So it's commercial malware. We knew that it was going to do things that were malicious, and we just had to figure out exactly how it was doing that. But it's a perfect example of our methodology of APK analysis, looking at permissions, to runtime analysis, then finally to static analysis, can really say, okay, where do we start? Let's narrow it down. Is it doing anything immediately bad? And then finally to the static code analysis. And as I promised, all of the texts and one-liners and all that are online at dshot.net/Android. So with that, I'll go ahead and turn it over to Matt, who will talk about DEX analysis.
Hey guys, so I'm Matt McDevitt. I'm here to talk to you today about DEX analysis. Basically what I do for McAfee is I do mobile malware analysis, reverse engineering, malware detection, basically anything having to do with analyzing Android applications. I pretty much do that. I also have a specialization in x86 and embedded system malware analysis. So, moving forward, I'm just going to jump straight into it and start talking about the DEX file format. Basically, what we have here, it's pretty much the same as the Java file format. We're going to be looking at headers, string IDs, method IDs, anything having to do with string data. That's all in the DEX file. So using this data, we can figure out what that DEX file is actually doing. In this talk, I'm mostly going to be focusing on methods, method IDs, because that will actually tell us what objects are being used within Java. So reading Java, as I said, we're going to talk about methods. Here's the package. Here's the package name, the object name, and then the method name. As you'll see here, there are 3 I's. What do those mean? Well, those mean attributes. So, for each method name, there's going to be a certain number of attributes associated with such. And then there will, of course, be some type of value at the end. Our value here is Z, which is Boolean. I'm going to talk about that next. And then we have some fields, which are basically the same thing, but it's more pointing to the Java fields. So, reading Dalvik. So these are all the different types. We have voids, booleans, chars, integers, floats, so on and so forth. I think you get the picture, right? So very first thing that we're going to discuss is hello world. This is probably the first DEX file I think that anybody will ever look at, hopefully, so that you have some type of idea of what's going on. Okay, so basically it creates the object of hello world. That's the string. Hello world is going to be the string that's going to be displayed. Invokes the stack method, which is make text. You can't actually see those last letters over there. But then it moves that result object into the register B0, and then invokes the virtual method, which is Boolean show. Okay, and then returns void. I didn't actually include any of the other invoking code within the Android DEX file, but basically what happens is it invokes the terminal program, which actually shows hello world as soon as this is run. Malware samples galore. Okay, so I'm just going to jump straight into talking about malware now. Now that we have some kind of clue of what the DEX file looks like when we're actually analyzing it. The main differences, well, actually there are no differences. Malware for both x86 and malware on Dalvik are both doing the same types of things. Okay, they're mostly out to make money. Okay, these are ransomware, all different types of stuff that also goes on the Android platform. So it wants to steal data, and then send it via HTTP post or to JSON. Okay, so data stealers come in all different types of packages. Sometimes they're CNC, sometimes they're not. Sometimes it's just like back and forth communication between the server. Premium service abusers are pretty much the same thing, except this one is just going to be calling a number and then just basically just charging you, $250 or whatever, and then that bill is actually given to you by whichever provider it was. So mostly these two types of malware are usually connected. If it's stealing your data, it might as well also numbers make some more money. Permissions. So in this particular piece of malware that I analyzed, I'm about to talk about it in a second. It had access to send SMSs, receive SMSs, write to external storage, which is your SD card, install packages, delete packages off the phone. I mean, you're pretty much dealing with something that has full capability of your phone. If you have root, of course. So, and I know in the recent version of Android, they said you can, they said that it doesn't give you root privileges automatically. Well, that's it's kind of another thing I can talk about later. You can actually just remount it. Anyway, but you can call phones, do whatever. Contact stealing. So basically what this code does, if you can see it, follow along. The top, it does move to next, so we know it's going to be looping. It's going to be looping this code. It's going to get strings, which are actually the contact names, and then it's going to use the string builder to create phone calling, and then number for that. And then it's going to move that result object to a string, and then it's going to print it out to another place called phone book, which we're about to talk about in a second. This is actually where it sends the contacts. So now that we've created the phone book with all the contacts in it, the phone numbers, the names, now it's going to use the phone book. It's going to get the default parameters, which were actually set by the CNC server. Now, in this particular piece of malware, the malware is dead. Meaning that when I got to the malware, all the domains where it's actually giving you the settings, it didn't exist anymore. So unfortunately, it was shut down. But as we can see here, though, just from doing static analysis on this one piece of the malware, because it is obviously a two-stage. So what they were going to do was send more configuration data, possibly install more packages to the phone to do other malicious activities. So as soon as we have the settings in there, it's going to send those contacts via post method, as we can see here, and then it's going to it's going to move the objects into the packets, and then it's going to get the response code from the server and say boom, disconnect, done. Okay. This is actually a creation of those SMSs where it actually gives the CNC server some important information about the phone. It gives it the IMEI, it gives it the IMSI, SID, and the version. It uses the string builder to push this into a text message, and then it sends it out. It appends all those things to a text message, and then sends it out via strings. So another piece of this malware, it had the ability to make calls from your phone. This is everywhere. You can seriously pull this from anywhere on the net, and everybody pretty much uses the same method to make a call. So the funniest part about a lot of this malware is that it can simply be copy-paste malware. It really doesn't take a lot of skill to build this kind of stuff and then have people install it to their phone, because people know what they're installing. You're not looking at the permissions. So basically what this does is it does an Android intent action call, and then it initializes the call using a number, which it actually parses here, and then it initializes the call. Unfortunately, I wasn't able to get that number because that was actually never sent. Those domains were dead by the time I got to this piece of malware, unfortunately. Yeah, that's pretty much what I needed to talk about in regards to DEX analysis, doing some static code analysis. There's a lot of malware to look out there, and I could probably list like 10 or 20 different malware repositories like off the top of my head. So going on to talk about heuristics, here's Jimmy.
So we covered data analysis, network analysis, tearing apart various malware statically, dynamically, seeing what it does. Now we're going to talk about what happens. We're back to heuristics. We're going to move back to heuristics. Work with malware, work with mapping, the same kind of stuff, analyzing malware, taking it apart, and finding automations. So my question is much the same, mobile malware analysis. I don't do Java any more than either of these guys do. And let's see, back to the actual problem. So we're looking at 1 million apps, right? We don't know if any of them are good necessarily. All of them are good. So how would we find out? We can do it by hand, and 1 million apps is a heck of a what do you call it? A time sink. Also a giant, really giant haystack. So we can do it manually and it'll take us forever, or we can automate it and actually save some time. So the concept is, what are we looking at? We're looking at heuristics, rules of thumb, ways of deciding how do I know that this particular APK I'm looking at is something I should worry about. I mean, say some of those social apps that look at all your permissions, they get everything and pull everything off your phone and send it off to who knows where. They want all your pictures, they want all your emails, they want your SMS, bad things. So one idea is, okay, if it asks for a lot of permissions, it's probably bad, but David covered that, how that's a bad thing. That at some point, certain apps are overly seeking your permissions. They want all permissions, they want to be able to do whatever they want on your phone. They may want a feature, features, is that what we're calling them? I mean, I don't want to call them features, but you know, they want the information, they want the access, they want it now instead of waiting until they actually do the work and build it out. So is it true that bad apps use a whole particular set of permissions? Yes. So the good apps. So it's not necessarily the best heuristic you can use to find out. We took a look at a bunch of apps and it's like, okay, there's nothing really incredibly unique about a particular bad app versus a good app. And it's very easy to have false positive on a good app, or in cases of, say, a social application. It just asks for all permissions. We probably tag on that and we take off a whole bunch of users, or take off the company. And I mean, we don't want to do that. I mean, people like their social networks, don't they? But yeah, what we do look at is this, what can we do for permissions in general? We're looking at a bad acting malware. I put together a tool called dump XML. It'll dump pretty much everything from the Android manifest.xml file that David was talking about earlier. So that's like a file that's all XML, and you could walk through the whole thing, or you could just parse and say, I want all the intent. So like say, okay, what can I fire off to this APK and make it do something? Or what if I want all the permissions? In this case, permissions, you feed it our heuristic scan for permissions, it'll give you a listing of what you have. In this case, we're looking at a particular a phone book inspector, stealer, or whatever app, but basically a data stealing app like Matt was talking about. It steals up the information and it sends it back to the attacker. What kind of permissions is it use? It's using the internet access, it's using your GPS, the just find location. I mean, there's course location, which is just whatever, Wi-Fi, whatever location, whatever Android feels is good enough to figure out where you are. And find is GPS, of course. So it's using GPS, using internet access to send stuff back, and it's reading other, well, technically starting first with reading other contacts, sending it back out, and sending your location. Kind of suspicious, but also could be used by something else. We would then send, this basically just gives an idea of how to look at this particular app. And of course, since these permissions aren't incredibly unique, it isn't the best way to do it. But it gives you an idea what you do with them. Oh, sorry, is that a question? Oh, sorry. Okay, another idea is, let's look at the developer certificates. Every APK on Android is signed by the developer. This isn't like a one location like in your browser where you've got an SSL certificate. It's not like one particular root server signs everything and says, this is good, this is like the proper app. These are basically self-signed certificates. You can do one yourself and sign your app and push it out there. And it's good to go. The only thing this certificate actually does is verify that whatever updates you push to the user's phone, they came from you as a developer. That they are yours. That's what it does. So what that really means is, so we can't necessarily say that a particular app is good or bad via the certificate. We can't say if we found a bad app from the developer, we can blacklist his developer certificate, her developer certificate, and say, okay, that's bad. Why don't we block all the apps in that developer because they're probably just as bad. I mean, they could be innocent. I mean, that's one technique attackers use. They'll put out an innocent app, get a whole bunch of followers and users, and then all of a sudden, the next version or the update or the next app you release, because they have such a good reputation, will be the one that does the bad acting, does the stealing your contacts or writing things over. I mean, it's what you do. So I mean, the one catch though is, I mean, where we coming to when we look at heuristics is, okay, what are these are all the good things. What are the things that cause us to false positive on this? With certificates, they're good if the malware attacker is using the same certificate writing like 100 different pieces of malware that do different things. They're likely not. They can do one, and we're probably going to catch them and detect them, and then boom, and Google will detect, and we'll see, okay, we're going to blacklist that developer's account, and they're no longer making any more apps under that certificate. So it's good if they're doing like a big blast of all these apps out there. If they're doing 1 or 2 apps, so they're not just going to doing a hit and run, not as useful. So we would FP on that, but it is, okay, by itself, it's not really unique enough as the game is. You have something that indicates something. It's really something you use as an additional indicator of basically is that bad. So let's actually look at another idea. So that certificates, how about, actually let me show you an example for us what that looks like. In case they have done 100 variants, say like the typical malware family fake variant, which is pretends to be a fake installer, which pretends to be an installer for various legitimate applications, but it really doesn't install them. It is pretends to be, so hence fake installer. We run about 25, oh sorry, is that a question, Michael? Sorry, people are stretching and whatnot. I mean, people are coming through like long flights, you know, so you don't stretch. So fake installer picks up basically we have a list in the tool itself of basically a whole bunch of our current listing is about 250 odd certificates from bad apps or actual malware that we've identified. So we know that if it has that certificate and it was written by the same person, it's probably a variant of that or from that same author. Very likely. Does he catch everything? No. It, once again, can be or can be become useless because no one detects anything. But we move on to that. Another idea. Multiple indicators. More than one of these heuristics. I mean, okay, if we have, okay, say, like if you're looking for a corp, okay, so we know that, oh, it's a dude, so it's okay, he's male, he's got, okay, and we know he's got like long hair. Boom, okay. We can identify this person has a bunch of indicators. If we just say, okay, he's a man, and we have like an entire line of people, useless, we're not going to find anybody. But the more indicators we have, the more unique they are. Like, okay, he has like an eye patch on because he had one eye missing. That's more helpful. We can find them a little easier. The concept is we add more and more unique indicators, or that can be relatively unique, or a mix of slightly less unique indicators together. The combination should be less unique, and I forget exact. The percentages aren't exact because once again the heuristics aren't totally exact. So you can't just say, okay, this is the percent for detection for that one. It's the failure rate for that particular heuristic, and we just multiply and get an answer. It's more messy than that. Okay, so once again, if we mix the couple of things like certificate matching, like permissions, put them all together, we come with something like this. You're running a tool where you run heuristics against another particular sample. Well, actually the same sample, fake installer again. What do we have? We have both the permissions and we have the variant, but it's very likely variant because it has the same certificate. This is really likely going to be something bad. And it's something we run it against say 1,000 apps that we know nothing about, and this comes up for like 3 of them. We're going to take a look at those quickly and say, okay, we're going to mark those all as fake installer. We're going to be exposed thinking that's fake installer. Is it likely it's not? Yeah, because we've seen 1 or 2 apps that are like from authors where they've written different malware related, or they've written a downloader and they've written like a data stealer. So you work with 2 different types of apps, and they have the same certificate. So this would be one of those cases where you can detect. The nice thing is it tells you something's bad. It tells you also the permissions-wise, what should I be looking for? What should I be worried about? And then you have a better idea. So once again, you get the sex of the offender. You have the any scars and marks and whatever it's got on. And you have a better idea who did the crime, or who's likely to offend. Well, not offend, but I mean, you get the idea. I mean, at some point that analogy breaks down. Let's move forward a little with that. The actual tool itself is dump XML. It should be on, I think, Assembly. I might have to release it. It might be still private. The tool itself is pretty straightforward. It'll either you can dump out a printable version of the Android manifest XML. Since if you just unzip an APK just by itself, you end up with a binary XML version of Android manifest XML. You can use tools like the David mentioned, like APK tool. APK tool will convert it from using an internal routines tool will convert from the binary for XML format to text, and you can read and look at everything there. So what we have there is you can also dump out the string table from there. You can pull out any interesting string, which is nice, somewhat useful. Or you can use the later 2 options, permissions and intents, so you can figure out what the permissions are and intents for a particular APK without doing the APK tool and all over. Basically, it'll give you like 2 minutes. Boom. That's what I'm looking at. Okay, maybe not. I'll look at something else. And then the heuristics thing is the last one, which one's the multiple heuristics. We'll be adding more of that as you go along, but I think that's tool in a nutshell. Sorry, question?
I was wondering, did you say that you implemented the AML parser library as part of that script? If you're able to convert your binary to standard XML, or are you relying on APK tool to do that?
Okay, the question is that is the dump XML doing the parsing itself, or is it relying on a tool like APK tool does? To convert the binary Android asset, the binary Android manifest XML to text. It does it internally. So you just run this one tool against it, and you've got. If I needed one of these, and like I didn't want to run an APK tool, like just wanted to know, and so I did that. Actually, I think do we have any questions now for all any of us? Yes.
Just a quick, in your experience, have you observed any of the data files that are encrypted, trace was in static analysis, or is there an issue?
Yeah, most definitely. There are a lot of APKs currently that are encrypted. Back when we made this talk, ridiculously enough, this was only about a month ago, and now there are actually commercial cryptors for APKs, which actually will encrypt the text file and everything like that. So you actually have to figure out yourself how to decrypt those APKs. I think there's like 3 widely used commercial cryptors, and there are also a lot of cryptors that people build on their own time. And a cryptor for that matter just moves byte values around. It just makes it really difficult to read it. And sometimes we'll have some server-side polymorphism, which just mutates the APK. The same malware, it just mutates it. It just moves a couple byte values every time new malware is created. So,
You were talking a lot about like the DEX file format. Do you find that more useful for analysis compared to something like a intermediary language like Somali?
You can definitely use Somali, but at the same time though, sometimes the malware will break Somali. Okay, so if you're actually dealing with a complex piece of malware and it breaks Somali, you can't look at anything.
You mean it doesn't run in Somali, or like maybe it breaks Somali?
So once Somali tries to actually interpret the code, the code actually breaks Somali. Like any other type of program, there are certain vulnerabilities that can be used. Even in great commercial decompilers and things like that, there are things that will break this. Even like ID8 Pro or what have you. There are certain type of code that will break. Will disallow you to look at the methods. Yeah, but on that note, Somali's great. Honestly, for most of the malware that you're going to be looking at, in case you want to do this, Somali's great, for sure. I've used it a lot.
That guy.
How do you do analysis when the malware is SSL?
What? I'm sorry. Say that again.
When the malware use this, how do you
Is there about SSL?
Oh, yeah, that's pretty good.
You get really upset. It's a problem. Here's the good news, and then here's the bad news. The good news is, the bad news is there's not really a whole lot you can do if it's implemented correctly, to the best of my knowledge. The good news is that we looked at, for sort of researching this talk and trying to find good examples, we probably looked at least 100 known malware samples, and I don't think we found like actual SSL fitting on any of them. We did find sometimes like a checksum that would push out basically that same error that I was showing when we were going over Android proxy. But fortunately, the ones that we saw were on the front end, and we could literally just click continue, and everything was fine. But a very well implemented SSL thing, you'd have to probably pass it back to Matt to talk about like runtime injection, because you'd have to do some crazy stuff to make that work correctly that I don't have experience with. Do you have an answer? Because that'd be awesome.
Can I just suggest one thing?
Yeah, please do.
Android, the new substrate toolkit, which is something that looks into like underlying like the Zygo process, so you can actually book an app or makes those substrates.
right? Yeah, that's
It's
right.
like, don't use SSL.
Right.
So you make like
Right.
an SSL kill switch in iOS.
Right. Yeah, that's what I was going to turn over to Matt. But basically, that was the same idea. That if you can hook it that way, then that's basically what you'd have to do.
It's like there's like a couple of ways we can put it, which is great.
Did you hear that? Anyway, any other questions? Yeah.
The talk today was focused on analysing one app at a time and pushing in the question about whether there's any evidence of multiple apps being used as an attack vector rather than one single app.
Are you talking about for the tool that Jimmy wrote?
Just in general, just in terms of having multiple Android apps that work together to conduct an attack rather than one single app.
Have you guys seen it?
Sort of. We've kind of seen apps that work together to do bad things. The closest thing we've seen so far are downloaders, so we'll have one piece of downloads and an app that does more things. Or we'll have a backer that sits there and does things after that. But not necessarily things that go pull together and like, okay, this one does one thing and this one does another thing, and they put it together and use the magic and do something much worse. Not quite yet in that manner, but currently we're seeing downloaders and additional functionality coming in, but not the fancy Voltron type technique where they all come together and destroy your machine, or destroy your phone.
Yeah, there is lots of, yeah. I'm sorry, I had trouble hearing the first like 3 terms. It's still early. Anyway, that's why I'm blaming them.
Yes.
But yeah, that's actually what we call two-stage malware, where it'll grab the first part, which will actually just download. And when you're actually looking through the download code, it can be really hard to point it out. You're like, where is this thing where it's actually going to download? But we can always tell when the piece of code says install packages. When it says install packages, and you're looking at the code, and it, looks like it's mostly ads, or the program doesn't work, it just does a bunch of junk. But it also has this ability to install packages. You might want to look at that down like a little bit more deeper to figure out if it's actually downloading an APK from a third party, and then it's able to install an APK. So, any more questions, anybody?
One more. Where'd you get 1 million APK?
Where do you get 1 million APKs?
Ask Google really nicely.
Did they give that to you?
No.
You didn't ask myself, I guess?
The Google Play Store.
Yes.
Yeah.
Expand on that. Okay, so you can scrape the Google Play Store. You can find other websites that may be hosting those. And we found that if we're looking for known malware, obviously malware repositories, malware loops, stuff like that, have a lot of Android malware that we can actually look through. Further than that, since a lot of these apps are actually distributed through third-party app stores, finding sort of illicit app stores in like China and Russia and stuff like that, where they're basically just, hey, use our app store and then you don't have to pay 99 cents for this app, has a significantly higher infection rate, as you might imagine. I mean, they're going in and cracking it anyway. They're like, well, I'll just harvest some data too. So we did use various sources. I wish it were easier for researchers to say, hey Google, could I get this? I promise I won't pirate them, but I don't think they would have necessarily let us do that.
I mean, and seriously, it's just as easy to, take Python and write a 50-line script to actually just crawl, APK websites.
Yeah, we had a.
And there are seriously hundreds of them out there.
Yeah, we did it with the wget, just downloading everything that ended in APK from an app store. Just had it wait like 1 second between requests. It was fun. Anything else, guys? Okay, I couldn't tell if you're raising your hand. Thank you.